Okay, now. So right now, I'm not gonna be starting that review. I'm gonna leave that for 3 p.m. today. Alex, chapter 12 is on the exam. Yes,
Yeah.
yes, chapter 12, because of ethers and epoxides, all of 13, all of 14. So yeah, you basically have the exam on 3 chapters. But right now, I'm gonna leave those 43 practice problems for the actual review. The practice problems that we're gonna see in here are from your actual extra credit quiz. And there's only 8 questions, but less than 50% of you got them correct. So that's why I chose them, and we're gonna go over them. Okay?
This is also on Canvas right now.
This one is not on Canvas. I forgot to post it. So we're just gonna be looking at the screen.
But you'll post it after.
Yes.
Oh, this one was on the practice test. This one was good. I like it.
So yeah, okay.
Can I do it? I like this.
Volunteer right away. Okay, awesome. Let's go.
That way I make sure I'm right, and if I'm wrong, y'all can just laugh at me. Enlighten me. All right, so we got, this is the acid, so it cleaves this primary versus this secondary. And if you remember, the acid is primary over, or third tertiary over primary over secondary.
I love to break down.
No, I'm convincing myself, though. I gotta convince myself.
Keep going.
Right, so then you gotta cleave this right here, right? So then you protonate this oxygen, right? And then you're still left with this negative on the iodine, and then the iodine kind of just comes in there. So then you're left with this one.
Beautiful, and that's the correct answer.
That's smooth. I love
Did any of you get confused with that question?
No.
Do you get any other answers other than 2?
So does it always cleave right there and then it adds the iodine to whichever?
So yes, remember, this is an ether. Now ethers, normal ethers are only gonna be cleaved in acids. What happens if I have the same molecule, but instead of giving you HI, what if I give you NaOH?
So that's a base cleavage, so then it goes primary, secondary, tertiary.
It's not gonna happen.
Cycle.
Exactly. Normal ethers are not gonna be reactive in bases, only in acids. We know the ranking that it's tertiary, then primary, then secondary. So that's why we're gonna be cleaving the one on the right. So we know that once we cleave this bond, basically that's going away. So that means that the oxygen is just hanging from that secondary carbon. So we're just gonna protonate it. We're gonna protonate it with whatever hydrogen you're given in the acid. And then remember, once you cleave that primary carbon, technically you're creating a little carbocation. So to make it stable, that iodine minus is just gonna be attacking there and getting connected in there. So that's why option 2 was the answer. Did anyone get this question on the practice exam? We got them? We didn't get it? We attempted it, but we didn't get the answer? Okay, but now do we see why that's the answer?
Yeah.
Okay. Yeah. So far, no questions. Yes. This is a normal ether. Remember, only epoxies are going to be reactive in acids and bases. So whenever you see that little triangle, that's when it's going to be really reactive. If you see anything else, only in acids. Any other questions for ethers? So far, we're good? Okay, we're good. Okay, this one. This was a little bit sad, actually. It's IUPAC. It was a little bit sad. Volunteer to show me the name. Okay, let's use different volunteers.
Sam, I am. We agree next to it. There you go.
So would you put the cis and trans after each respective, like?
You have to put a parentheses indicating if there's cis or trans. Before.
2,4,6, and then like trans, cis, etc. Or like whatever.
Versus the relationship. So 2 cis, let's say, I'm not sure if that's cis, you tell me. Then you fill out that parentheses, and then after that, you just put wherever you saw the double bond. So 2, 4, and 6, and then you give me the carbon chain. And remember, exactly, we're using E and C, cis and trans, we're not using them anymore.
And this one is using ones.
2E, comma, 4C, and then 6C, correct. So far, we're good.
Is it non-trying or trying non?
What do we think? Did anyone get this question?
I guess it's fine. I don't know what that
We got this question? It is gonna be trying. Remember, like, we use die to indicate that we have 2 double bonds, we have to use try to know that we have 3 double bonds. And great job, Sam, you got it.
So it's not try non, it's non.
It's not try.
Non,
No, no, try. Right.
There we go. Sam, great job, Sam. Okay, questions on IUPAC. You should expect some questions naming alkenes. Remember, all of chapter 13 was with alkenes. So yes. Yes, remember the whole goal with IUPAC is to get the lowest locus possible. To find the parent chain, remember, we're looking for the longest continuous carbon chain.
So. can
Yes.
I draw an atom and we try and obtain the.
Sure.
Yeah, please.
Yes. Okay. So, let me see if I can do what it is in here. Okay, so if we're looking at the double bond over here between carbons 1 and 2, sorry, between 2 and 3, we see that on the right side, the methyl group is going to be my priority one. On the left side, I can see that the carbon from the double bond is going to be my priority one on the left side. So because both priority ones are pointing to opposite sides, that's going to be C. Sorry, E. It's going to be trans. And then same process with the rest of them. In this case, for the double bond between carbons 4 and 5, they're both pointing up. So it's C. And then the one over here, this one, they are both pointing down. So it's also going to be cis. So again, we're just looking for priority ones on left and right sides of the double bond. That's it.
That's it now, yeah. Yes, yeah.
Okay, so can we try and name this atom right?
The molecule, sure.
So would you start counting from here or here?
From up there.
Yeah, you got enough.
Exactly.
So the methyl group is a substituent,
But that's in naming, correct? Whatever we're looking in terms of numbering for like kinetic or thermodynamic.
Oh, that's a great question. If we're doing a reaction, then we have to start from the bottom to the top. Remember that? Your number 1 is going to be the lesser Gleichinder carbon. Well, double bond.
is that synonymous to less than 2?
Let's just hit it, yeah.
Okay.
Same thing.
We're talking about the reaction, it's thermodynamic.
And don't worry, we're going to see a lot of practice problems on kinetic in there.
Like IUPAC, you try to spend most of it. Alright, same.
That's what you're saying.
I get it.
Okay.
Gotcha.
Do you want to give it a try to the full IUPAC name?
Oh, this, okay. So it's.
Yeah, right.
Almost perfect.
Almost.
Almost perfect.
Cyclo.
Cyclo, exactly. If I don't write cyclo, then that's just going to be a linear carbon chain. There you go. Cyclopentadiene, and that's it. Great job, Sam. Okay. Any other questions on IUPAC? So far, we're good. Bless you. Okay. This one, your epoxide. Who wants to give it a try? Maybe someone else from the left side?
There's somebody from the back.
Emily? Give it a try.
This is cycle, it's not regular. So there is- One, two, three, four, five, seven, 4, 1. Right, with the base, on the base,
Yeah.
it's a base cleavage on regular, there's no reaction. But if it's regular, it's cleavage. Right.
Acid as well. It doesn't matter if it's cycles or not.
Yeah.
Mhm.
That's nasty. Wait, no.
No base.
The base, yeah. the
It's a base.
base. Oh, yeah.
It's an epoxide. Remember, triangle, it's reactive in acids and bases. Triangle reacts with both. We're gonna cleave that primary carbon.
On that.
All three good, all six. Yeah.
No, go for it. Take your time. It's okay. It's in condensed formula. Draw it out, yeah.
No, it's right, west axis, previous is 312. Or area.
Take your time. It's okay.
Whatever would, yeah. Yeah, you can put any other. Yeah, the two levels.
Bro, we need to start from the substrate and the bottom, correct?
From the solvent, yeah.
So,
Right, so then the eight to the bottom.
another C.
Here, that one.
So far, you're good.
Free floating. It's not gonna happen.
So when you cleave it, right? So let's say, see that primary, there's two hydrogens out there, right? When you cleave it, it leaves that cation. Okay. You see what I'm saying? You're gonna attach the methoxide to that primary.
Did anyone get this question
I-
on the actual exam? Did you get it, Alex? And you, Geraldine, as well. 1, 2. Do we all agree? Is it gonna be 5? What did you get? What did you get, Juan?
5.
5 as well? Okay, so we all agree with 5.
Yeah, there's 5.
It is gonna be 5, yeah.
You see that?
So as long as you know where to cleave it, you should be good. I know that condensed formula is a little tricky, but as long as you count your carbons, you should be good. So it is gonna be 5.
That, like, yeah.
Okay, so for the mechanism for base cleavage, remember, we're always looking at those carbons directly connected to the oxygen. The one on the left, we know it's primary, the one on the right, tertiary. This is the ranking for base cleavage, so it makes sense to cleave that one over there. Now I'm gonna keep my primary and my tertiary carbon over here. I have my 2 methyl groups and I have an oxygen minus. That oxygen, it came from the epoxide. Now, on the primary carbon, remember that the base is also gonna act as a nucleophile. So we're gonna do a nucleophilic attack, which means that it's gonna get connected in there. So now I have an oxygen with a methyl group. Now, after that, we know that the very last step is just gonna be with our little solvent. So everything can be neutral. So that oxygen is just gonna grab one of those hydrogens. Now we have this guy. So that was the mechanism. And then to find them incandescent orbit, again, just count your carbons. We have one carbon over here. We have our oxygen next. Then we have the primary carbon. Let's just label it number 2. And then my carbon 3, which is the tertiary one, it's over here. That carbon is connected to 2 methyl groups. So let's label them 4 and 5. And then the little OH group is just over here. Okay. Questions? Do we all get it?
Makes a lot more sense.
Makes more sense.
It's not the usual.
Oh, yeah, the Williams one. It's like,
Okay. Let's look at the next one. Okay, it was this one. We're looking at the molecular orbital of benzene. So that's from chapter 14. And they're asking how many pairs of degenerate pi anti-bonding molecular orbitals there are.
2.
It's just gonna be 2. We have 2, but
So the ones that are like low better.
read the question carefully.
Oh, wow. It is anti-bonded. So,
it's,
Wait, generate anti-bonding,
Yeah.
so there's one.
Well, is it ground state or is it excited? Because ground state is just.
Remember that the labels always remain the same.
So it's 2.
I just say it's 0.
Because there's 2 anti-bonding. Yeah. 2 anti-bonding right there. And the ground state
it's one pair.
Yeah, 1 pairs or okay.
Pairs, there's only 1 pair. So the answer was just 1 in here. That's why I told you guys, read carefully. The first time that I saw this question, yeah, I initially thought it was 2, but it was marked 1 and it makes sense. We just have to read carefully those
Yeah,
questions.
Oh, the order.
Yes,
Oh, no.
Yeah.
You just, there's 2, but there's 2 like orbitals, but it's in pairs, so it's one of them pairs, so. I'll do it, same level.
okay, so let's break down that question. So first of all, degenerate, it just means that the orbitals are in the same energy level. And then they're asking for anti-bonding orbitals, so we're only looking from pi 4 until pi 6, the ones on the top. We have 3, but in this case, they're asking for how many pairs we have. Pairs, it just represents that we have 2. So that's why it's gonna be only 1 pair, because the pair
I mean,
constitutes of 2.
if it wasn't a pair, it would be 2.
Yes, if you don't see pair, then the answer should be 2.
Is the energy level the same from pi 3 and pi 4?
Pi 3 to pi 4, no. Pi 2
I
to
mean,
pi 3, yes.
Yeah, so that's what
Yes, those two are the same energy level. Okay, let's look at this one. Which one is an untrue statement for Diels-Alder? Take a few seconds to read that one. Do you have an answer?
I know it's not this.
Yeah, probably.
So yeah, it is gonna be A. Because remember, they're just asking you for the false statement. That's it.
Okay, yeah.
So we know that the exo product is not going to be the major one. That's the least stable product that we could possibly create.
Right.
We always want to try endo. Okay, this one. Which one is aromatic? Do you all think it's going to be one?
Yo.
It is going to be one. How many pi electrons do we see in molecule one? Okay, we see 6. So that means that it's following Huckel's rule. So of course it's going to be aromatic. What about molecule 2? How many pi electrons do we see?
4.
We see 8 pi electrons. So it means that what kind of system do I have?
You said 4.
No, molecule 2. For molecule 2,
I'm pretty sure.
we have 8 pi electrons.
Hey, I got it.
If I have 8 pi electrons, what kind of molecule do I have? It's anti-aromatic. What kind of system is molecule 3?
That's cyclic.
Just non-aromatic.
Non-aromatic.
Molecule 4.
Non-aromatic.
Beautiful.
That's fine.
And then molecule 5.
I think it's-
Not even conjugated.
No, it's anti.
Oh,
non-aromatic.
wait.
It's non-aromatic, actually. Remember, single bonded heteroatoms, they can choose to be sp2 or sp3. If they're sp3, non-aromatic. If it's sp2, how many pi electrons do we see?
4 and
With SP2, you're given 6. SP3, you're given 4.
F3.
Oh my God. Okay, let's rewind really quickly. So the rule with heteroatoms, we are only talking about heteroatoms that are uncharged. Everything is stable. We don't see any pluses or any negatives. In this case, we see that nitrogen with a positive charge.
Oh.
So in this case, we're not going to be following the heteroatom rule. It's going to act like a little carbocation.
Oh.
Now, it is fully conjugated, but now I have 4 pi electrons, which makes it anti. So yeah, be careful whenever you see any charges.
It doesn't get the.
If you see any charges, then be careful.
What do you mean be careful? It's
Like in that problem,
Okay.
we have a single bond heteroatom, but we see a positive charge in there, so it's gonna act like a carbocation.
So it does not conjugate, it's it's stuck in that configuration.
Yes, but it is fully conjugated either way.
No, like, it doesn't get to pick, that's what you guys can pick.
Yeah, yeah.
Question, for the intermolecular Williamson ether synthesis, are we supposed to know the mechanism? Cause on the quiz, on the practice quiz, it wasn't really asking us for mechanism necessarily. It was just kind of asking,
It did have to like, what the term was called.
yeah, it was like a couple questions like that, but no
Yeah.
mechanism based. Are we supposed to know?
I think you got it right, not the mechanism per se, how the atoms move, but the name of the mechanism, yeah,
Yeah, I got it right.
it was very simple.
Yeah, it makes it ether with its own cycle, its own cycle.
Mm-hmm. Okay. Let's look at this one. Which diene can undergo Diels Alder?
Is.
What were the requirements for a diene?
Conjugate,
It has to be conjugated, what else?
non-sterically hindered.
Non-sterically hindered and.
It can be rotated, it can be supersist.
It has to be super cis, exactly. Now, in molecule 1, what kind of system do we see? Conjugated? It is isolated, so this one is not gonna work at all. Molecule 2, what kind of system? Isolated as well. Molecule 3, what kind of system? Conjugated. This one is S trans. Okay, so let's look at it individually. Remember, single bonds can constantly rotate.
It can be that, but so.
Now, we can get it into the S-cis conformation, yes. But there's too much steric hindrance because of those method groups.
So do you have,
So-
like? I originally got confused with this, but is it sterically hindered when you look like where the hydrogens would be? They're kind of over top each other.
It's not necessarily about the hydrogens. It's about your orbital groups over here.
Yeah.
These guys, they're clashing each other.
Yeah, I guess.
So it's gonna be, they're gonna be like right on top of each other.
Yeah. So that's-
So molecule 3 is not gonna work for that reason. Molecule 4, we know that it's conjugated. Is it super cis or super trans?
It's trans, but you can heat it up, cook it,
But I can rotate it. I can rotate it.
uncook, yeah.
So this one is gonna be your answer in this case.
Yeah.
And then last one, molecule 5
That's nice.
is just isolated, exactly. Okay, questions? Yes. It has to be conjugated and it has to be as cis. Yeah, and then you always have to think about steric hindrance.
Yeah, 'cause the fourth of that. and third, fine.
Did anyone get that question on the exam? Well, on the practice exam?
Like so.
We got them? Did we get them right? Awesome.
Always.
I almost chose 3.
Mhm. Okay,
That's what I did, guys.
Yeah, because the conjugated, but then 2 is not locked in that tray. Yeah, 4 is locked in that tray. You just gotta cook.
Lisa?
When it, you just isolate it.
up to the other one, yeah, no problem.
Like it could work, but 2 were better.
Okay,
So I think
who got that question?
2 were definitely not better. You're telling me a.
Do we know the answer?
It's locked in S system.
Okay, I have one vote for 2 and one for 1.
You had to pick one.
For 2, okay, I have 2 votes for 2.
So would 4 work?
Yes,
In terms of reaction speed, which one would be between 2 and 4?
2.
So 4 is locked in.
okay.
Oh, that's a good.
So in this case, it's not asking about the rate. It's just asking which one is gonna react in diasolder. That's it. Now, let's look at each molecule individually. Molecule 1, what kind of system do we see?
That's isolated.
It's just isolated. This guy is not gonna work at all. Molecule 2, system, conjugated. Conformation, super trans, but I can rotate it, exactly. Is there gonna be a lot of steric hindrance in there?
No.
No, so this guy is gonna work. Molecule 3, what kind of system do we see?
That's isolated.
It's isolated, so this guy is not gonna work at all. Molecule 4, system,
I think conjugated.
conjugated, and it's super cis.
And it's.
As long as it's super cis, this guy can work.
Oh, okay. So, but the-
Yes.
In terms of reaction speed, which one would be favored between 2 and 4? Like which would 2? Is it because 4 is more steric than hindered?
It's because it's lesser hindered than 4.
Okay, but you still have to heat up the 2
You always need heat to promote that reaction.
in either case.
Yeah.
Oh,
The only thing that can affect the rate is gonna be electron donated or withdrawing groups. That's it.
okay, I got it.
Okay. Questions on that? We're good? Okay, did anyone else get any other questions that you want clarification on from the quiz? Take a look back on your attempt. The last one, it's 2 and 4. It's both. Take a quick look at your attempts. We have 13 minutes. Those were all the problems that I prepared for SI. Those are the ones that were not so good. Yes. So 3 is non-aromatic because it's not fully conjugated.
Yeah, it's not.
And then same process with molecule 4. Those 2 carbons in there on the top, those guys are sp3, so it's not fully conjugated. Yes. Can we draw them out? Yes.
Let's go.
So the way it works is caffeine. You see what cold.
Does anyone else want to draw their questions? You have any other questions? We're good? We're good?
You should like give us an extra 10 minutes.
Just extra 10 minutes. Because yeah.
Bro, you got a long hour in love.
Before we leave, Emily.
You said because the artist was chosen to a larger size.
Do you have a photo of the, does anyone have a photo of that problem?
Which one, what's the question here?
This question asked, like, if you can choose the endo exosome and then python. I guess I'm just confused with the exosome.
I think you guys know what she's talking about, though. I'm not sure able to picture that problem.
Should endo mean that the artist would be closer to the starting?
So the larger bridgehead, the more carbon you get.
Yeah.
I can't see it from far away.
I know Ron's talking about that. Yeah, I'll take a picture of it. It's basically, it was like one of those bridge ones, and one side is longer than the other. Yeah, no pylon, nothing of that.
There's no python.
Yeah, it's just about that. One side is a lot of carbon shapes.
We let me redraw it here.
Yeah. It's.
Okay, let's look at this guy.
Essentially, your brain runs through.
Essentially not done,
Yeah,
in a way.
yeah. So just quick sugar.
So from SI, we know that endo, it's the major product, right? We want a trans relationship between the bridgehead and anything that we have in the dienophile portion, right? Now, in this case, we're gonna apply the same rules. Now, our bridgehead, it has a little R group sticking out of it. So this is gonna be a reference point. This guy is pointing up. Now, you have two rings that are just composed of pure carbon. So we can't really tell what's gonna be the diene or dienophile, plus there's no double bond. I'm not sure why, but
Yeah.
Yeah, he just said.
yeah,
Yeah.
in this case, it's the same process. Our group is pointing up. The largest ring, it's pointing down. They're trans to each other, therefore they're endo. Trans means endo. Exo cis.
Look at the other two. rings. Literally the one with the most.
Yes. There's only one bridge though.
I thought Endo was the larger bridge.
Do we have photos? Show me. In general, remember, what's the rule? We want a product that's not that sterically hindered, because that's gonna be more stable. So you can use that to kind of like figure out the answers on the exam. We always want something that's less sterically hindered. Right now, I'm waiting for the picture, yes. Yeah, it has a trend relation.
Oh, yeah, okay, so is that an endo if it's any larger than the Oh, yeah, yeah. But I know he uses this, but I know you're talking about this, right? Yeah. That way, it's a long time.
Just looks on the right side and the little R group.
Oh, no.
Okay, do we have any other last minute questions? We're good? Okay, I'll see you guys in the physical science building, room 109 at 3. So please go get food, 3 until 6, it's gonna be 3 hours, and get ready, we have 43 problems to go through. Sorry? I'm not sure, so we'll see.